Recent headlines in the scientific community have made bold claims about graphene breaking a fundamental law of physics. To understand the reality behind these sensational headlines and why graphene continues to captivate researchers worldwide, we need to examine what this material actually is and its place in modern science. Graphene has been called a wonder material since its discovery approximately 20 years ago, attracting intense scientific interest ever since. This remarkable substance consists of a single layer of carbon atoms arranged in a hexagonal honeycomb pattern. Imagine a sheet of chicken wire, but only one atom thick. Despite being incredibly lightweight and flexible, graphene possesses extraordinary strength and conducts electricity and heat better than most known materials. The discovery earned the 2010 Nobel Prize in Physics and sparked predictions of revolutionary applications ranging from ultra-fast electronics to advanced batteries in cutting-edge sensors. However, after 2 decades of being hailed as the future of technology, many of these promised applications have yet to materialize on a commercial scale. This gap between promise and reality has led some scientists to suggest that graphene has been somewhat overhyped. Nevertheless, new research continues to reveal surprising properties of this unique material that challenge our understanding of physics. A research team from the Indian Institute of Science recently published findings in Nature Physics that have reignited interest in graphene's unusual properties. They measured how electric charge and heat move through ultra-clean graphene samples and discovered behavior dramatically different from what occurs in conventional metals. In ordinary materials, electrical conductivity and heat transfer follow a well-established relationship known as the Wiedemann-Franz law. This law states that the ratio of thermal conductivity to electrical conductivity is proportional to temperature, arising from the fact that electrons typically carry both electric charge and heat through materials. However, electrons in graphene don't follow this conventional pattern. Instead, they behave as what physicists call a Dirac fluid, an almost perfect quantum fluid with the lowest theoretically possible viscosity. In simpler terms, electrons in graphene flow with minimal resistance, almost like a superfluid. This occurs because electrons in graphene interact much more strongly with each other than they do in ordinary metals, creating collective behavior that defies conventional expectations. The Wiedemann-Franz law, despite often being called fundamental, is actually a derived relationship that works well for most metals under normal conditions. It's an approximation based on certain assumptions about how electrons behave, and these assumptions simply don't hold true for graphene. The law isn't truly fundamental in the sense of being a universal principle of nature. It's more like a useful rule of thumb that happens to work in many common situations. So how new is this discovery? The truth is that violations of the Wiedemann-Franz law in graphene have been observed before. The researchers themselves acknowledge in their paper that graphene naturally violates this law and that previous experimental reports have provided valuable insights into Dirac fluid formation. What makes this new work significant is the use of exceptionally clean graphene samples with very few defects, allowing them to observe the effect with unprecedented clarity and precision. This represents a substantial improvement over previous measurements and provides the clearest evidence yet of graphene's quantum fluid behavior. The press release's mention of testing black holes refers to a fascinating area of physics known as analog gravity, or quantum simulation. The idea is that small fluctuations in the electron fluid within graphene behave mathematically similar to how quantum fields behave near black holes. This creates what physicists call an analog system, a controllable laboratory setup that mimics aspects of phenomena that would otherwise be impossible to study directly. However, it's crucial to understand that using such simulations requires assuming the mathematical correspondence exists. You cannot use the simulation to prove that the mathematics is the same. The connection between graphene physics and black hole physics, while intriguing, remains largely theoretical. From a scientific perspective, this work represents solid experimental physics that advances our understanding of quantum materials. However, it doesn't rewrite physics textbooks or overturn our fundamental understanding of nature. The researchers have performed careful measurements that clearly demonstrate graphene's unusual properties. But these properties were largely expected based on theoretical predictions.